it's a complex. It's a complex orbifold, and in fact, Teichmüller space carries a natural metric, which I will be discussing in a minute, in such a way that moduli space is a finite volume complex orbifold. So it's very closely parallels the case of Riemann surfaces themselves. So a more classical class of spaces that can be described in this way is that of locally symmetric varieties. Of non-compact type. Which they can always be presented. I will give a complex analytic definition in a second. But locally symmetric varieties, they're just locally symmetric Hermitian manifolds. They can always be presented as the quotient of a bounded domain which are known as bounded symmetric domains. And sort of in particular, they are homogeneous as complex manifolds, and the group of automorphisms is very large. It acts transitively of points. And so that V can be presented again as the quotient. And again, let me not write the definition of a bounded symmetric domain, but the class of those domains is the same as that of Hermitian symmetric spaces. And complex analytically, one can just define them by saying that there's a isolated, for any point there is an involution, a holomorphic involution, for which this point is an isolated fixed point. Using this involution, so one can deduce that they have a really large automorphism group. So the theme of comparing the geometry of Teichmüller spaces with that of locally symmetric spaces, it has been a classical, very fruitful way of studying Teichmüller theory. And in dimension 1, everything coincides. So let me introduce to save myself time, let me denote with the word BSD, the bounded symmetric domain. So in this case, Teichmüller space is of course a bounded symmetric domain. Which is just a unit disk with its Poincare metric. In higher dimensions, the situation is quite different. So it's known in this case that the automorphism group of Teichmüller space is discrete. That's a theorem of Freuden. So in particular, Teichmüller space is not a symmetric space. Again, just a historical remark. Freuden really proved this in the case where n equals 0, but he had all the right ideas. So later, there have been several other papers of generalizing that for any number of punctures, but the ideas are all due to Freuden. Okay, so in fact, Freuden proved more. He deduced that the automorphism group of Teichmüller space coincides with the mapping class group, that is, with the orbifold fundamental group of moduli space. And well, to my mind, what was Royden's sort of main breakthrough idea at the time was to study this question geometrically, and he introduced he studied the natural intrinsic metric of Teichmüller space in order to answer these questions. So let me say what this is. And let me point out that I still don't know, purely algebraic proof of this statement. Is why doesn't moduli space have any extra automorphisms without using essentially the Kobayashi metric on Teichmüller space. So for any bounded domain, excuse me? Convex in what sense? They are not convex. So in fact, I will mention some results in this direction. Give me a second. But yeah, but I'll get to this. Excuse me? Yes, it's a domain of holomorphy. But the boundary, it's not nice. So in fact, I don't know. It's not known even what's the simplicial structure of the boundary as a topological space of these embeddings of Teichmüller space in CN. In fact, they're not even unique. So there's a.
Yeah, but it's pseudo-convex, right?
Yeah. Well, in some suitable notion of pseudo-convex, yes. But the boundary is not smooth, so one has to really look at an exhaustion of pseudo-convex domains. Okay, so for any bounded domain, there is a unique metric which is characterized by the property that it's the largest metric. So that every holomorphic map from the disk inside the domain is not expanding. Or in other words, you look at all possible holomorphic disks, or holomorphic maps from the disk to Teichmüller space to a bounded domain, and then, you look at all, in a given direction, and then the longest vector you can get, you would like to use as a measurement of the unit for this metric. And let me just point out that, you can think of this metric either as a family of complex norms on tangent spaces, or as a distance function on pairs of points. And yes. For this particular, yes. So this is true. This is very general. You can study this for any complex manifold. Of course, the issue is that there might be directions for which the metric vanishes. But that's the only problem that can arise. So but for bounded domains, it's always non-degenerate complex Finsler metric. And the unit norm ball is convex. Okay. So what are some examples of this metric? Well, the first one is, of course, the unit disk equipped with a Poincare metric. It coincides with the Kobayashi metric. Or more generally, CHN, the complex hyperbolic space, can be naturally identified with a unit norm ball, with a round unit norm ball in Cn. And in this case, the Kobayashi metric coincides with with the unique invariant metric of constant curvature, holomorphic curvature. So it is a Kähler metric in particular. It's the Kähler symmetric. However, this is in some sense the only case where the Kobayashi metric is a Kähler metric, so one can already see in the bidisk, so the Kobayashi metric is the sup metric. Meaning the supremum metric arising from the two factors. And then the unit norm ball, well, it is clearly not a Hermitian metric, but even worse, it's not even smooth anymore. So it's not Hermitian. And not smooth. And the last example I want to discuss is that of Teichmüller space. In this case, the Kobayashi metric is, well, coincides with the Teichmüller metric. Well, which is a classical metric studied in Teichmüller space, well, studied from complex analysts at least. So let me tell you what the Teichmüller metric is, but before doing that, let me just mention that in particular, Teichmüller space with its intrinsic metric has the structure of a complete straight metric space. A complete straight metric space. Sorry.
What does it mean?
Oh, there's, well, geodesic. So there's a unique geodesic between any two points. So, well, once you fix a base point, one can think of Teichmüller space as parameterizing complex structures marked by a given, by the given base points. Or in other words, you can think of a Teichmüller space as a Riemann surface X along with a given isotopic class of homeomorphism from a fixed surface. So in particular, for any 2 points in Teichmüller space, there's a canonical homeomorphism. Well, there's a canonical, well, isotopic class of homeomorphism from one to the other, and then the Teichmüller metric, well, or rather the distance between 2 points in this Teichmüller metric is the So, well, since X and Y will be different Riemann surfaces, there is no conformal map between them. So one studies the quasi-conformal dilatation of any quasi-conformal map between them, and you try to minimize the quasi-conformal dilatation between two surfaces. So that's a classical way the Teichmüller studied this metric. Also, I should point out that the fact I quoted over there, the Teichmüller space is complete with this metric. It's really a theorem of Teichmüller, and it's not obvious from this definition. However, since I will not use this definition for the rest of the talk, I would like to give you some other ways of thinking about it. So in particular, the description in terms of the norms on tangent spaces, it's also very natural. So for any base point, the cotangent space to moduli space or Teichmüller space is naturally identified with the space of holomorphic quadratic differentials, which are global sections of the square of the canonical bundle. Or in other words, the extensors that locally can be written in the form QZ dz square. So in particular, given any holomorphic quadratic differential, there's a natural metric one can construct, which is given by taking its absolute value, which is going to be a flat metric away from the zeros, and that defines a norm on this space by considering the area of this metric. And let me mention that this is C1 smooth and convex. So by norm duality, the dual of this vector space has a norm, and that is that coincides with the intrinsic Kobayashi metric. So this norm on Teichmüller space is this norm is certainly not a Hermitian norm, so it doesn't come from an inner product. However, it does have certain similarities with Hermitian norms. So it's perhaps it's a surprise that both in the case of Teichmüller spaces and bounded symmetric domains, although these intrinsic Kobayashi metrics they are not Hermitian metrics, these spaces are abundantly populated by holomorphic totally geodesic copies of the Poincaré disk. So through every point in direction. So, in fact, if these metrics happened, if the Kobayashi metric was Hermitian, this property alone, would allow you to deduce that it has to be CHN. So it's a very strong property. So let me tell you how this arises in the case of bounded symmetric domains. Well, it is known that for any point and any direction in a bounded symmetric domain, you can find a holomorphic embedding in Cn, which is convex and circularly symmetric about this point. Which is classically known as the Harshchandra embedding. then you can just take a linear projection onto this. Well, since this is a convex embedding, you can just project onto this one-dimensional slice that you're interested in. And well, this one-dimensional disk, since it is given in terms of a retraction, it will have the property that it is totally geodesic for the Kobayashi metric. So maybe I think I forgot to mention, well, that the fundamental property of this metric is that it's non-expanding for holomorphic maps between any domains, any two domains. So in particular, if you find a holomorphic retraction, the image of this of the retraction will be a totally geodesic subspace, simply because you don't expand the metric. Well, inclusions are non-expanding, so the embedding couldn't possibly contract any vectors. Well, however, Teichmüller spaces don't, well, realizing Teichmüller space as a bounded domain, it's not possible. Well, you don't have these nice convex realizations anymore. But instead, one can use the holomorphic quadratic differential picture to produce a lot of these holomorphic totally geodesic disks. Yes, it's a totally geodesic isometry. So, well, given a Riemann surface and a quadratic differential, which will be a point on the total cotangent space, allows you to present the surface as a polygon. We can present as a polygon and define an action of the group SL to R on this space. So instead of writing down explicitly, let's just do one example, and I think that well, Alex's talk explained that very carefully yesterday, and most of you are probably familiar, but perhaps one of the most interesting examples is that of a genus 2 surface arising by gluing opposite sides. So for any element in SL2R, you get a new polygon with a new quadratic differential attached to it, and that will define a new point on a new Riemann surface along with a quadratic differential. And just forgetting the quadratic differential produces.
When you speak of polygon, you speak outside of the
Yes. So it's literally a finite polygon in the plane whose sides are paired, so that any two sides on the same pairing differ by a parallel translation, and you glue them either by this translation or by translation and rotation by 180 degrees. And the differential would be the one arising from the plane, this is squared. So in particular, this gives rise to since SO2 acts by holomorphic automorphisms of the plane, it doesn't change the complex structure, and that gives rise to copies of CH1 in Teichmüller space, which are known to be holomorphic and totally geodesic, and classically known as Teichmüller disks. Okay, so
Which direction does it go? Because there we have forgotten the
yes, so the norm duality gives norm duality gives you a canonical map from the unit norm ball on the tangent space to the unit norm ball on the cotangent space simply by taking the unique hyperplane which is tangent to that direction, and that's exactly the direction that Q corresponds to. However, this is a non-linear map. It's a complicated map. Okay. So, are there any questions about this? So, it was a folklore question which was open for a long time in the complex analysis, at least group of Teichmüller theorists, whether one can determine or construct this Teichmüller disk purely in terms of the metric of the Teichmüller distance, or in other words, is every totally geodesic disk necessarily of this form? And so the first result I would like to state settles this question. So every totally geodesic isometry is necessarily holomorphic. Or anti-holomorphic. And in particular, it is given in terms of these SL2R orbits. So what do you mean?
No, we just need. It's enough to say that it's isometric.
Well, in terms of the distance, of the Teichmüller distance, you can think of it as a metric isometry, or.
But the word totally geodesic. What's the purpose of that?
He's using isometry, I think.
Well, so so I should tell you what it means. So by isometry here, I think of the Kobayashi metric as given infinitesimally in terms of the Finsler norms of tangent spaces.
But it's enough to say that every isometry between the two metric spaces.
It's the same thing. If you want to use a Teichmüller distance, then you can just say isometry as metric spaces. But I would like to think of that as
Yeah, but normally when you say total geodesic, you mean the second one form vanishing. But here you do not define the second one.
It's a Finsler metric.
I think you can erase the two words total geodesic in your theorem.
Okay, total geodesic isometry for the Kobayashi metric, or for the Kobayashi distance function. However, I should point out that perhaps this result is interesting is because if I remove my glasses, in fact it's false. The reason is that there are hyperbolic planes which are almost isometrically embedded in Teichmüller space, and they're very far from being holomorphic. So there's So Slimer and Leininger, they constructed hyperbolic spaces which are almost isometric, isometrically embedded for the Teichmüller distance. And it's really interesting to.
I have a few questions. So that those ends are not necessarily the same end.
Yes.
But also, does your term apply to rescalings of the metric on hyperbolic line?
Yeah. If it's a conformal, yes. If it's a scaling by constant factor, and you assume it's a metric isometry or total geodesic isometry, then it does apply. However, it doesn't apply for for Riemannian isometries. So let me just leave it to that. So does this answer your question?
Sorry, what did you just say again? I didn't understand. What do you mean by not for Riemannian isometry?
Well, if you don't assume that it's an isometry for the distance, but just infinitesimally.
Oh, okay.
Then then the answer might be. In fact, it's plausible that one can deform these examples to get Riemannian isometries.
Oh, I see what you mean.
So we can discuss more. There's more to say, but let's.
So here I did not. So almost isometric embedding from the HN,
Yes. Into Teichmüller space.
So these maps are also holomorphic.
No, they're not holomorphic.
Oh, so they exist. Okay.
They exist and they're far from being holomorphic. Okay.
You're just ruling out something like Nash's theorem. I mean, that's why you want to say global isometry, not just Riemannian isometry.
Okay, so let me make several remarks about this. The first one is that this is classically known to be true. This rigidity statement. For rank 1 bounded symmetric domains. Which really there's just one of them. However, it is false for high rank. And let me just explain why this is the case. Well, in fact, one can see this already by looking at the bidisk. And I would like to choose the opposite complex structure on the second factor and take the graph of the identity. Then it's easy to see that this is a totally real disk copy of CH1 in the bidisk, which is totally geodesic for the Kobayashi metric. And this construction will actually come up in the proof of this result.
It's not irreducible, right?
Yes.
Yeah, so
You
require the pocket manifold to be reducible.
Well, yes. I mean, in the class of bounded symmetric domains, either you are CHN or you can find a totally geodesic holomorphic copy of the bidisk, regardless of whether you're reducible or not. Siegel space, for example, is reducible, but it has a lot of isometric copies of the bidisk.
If you rescale the metric, you have HN in there, which you have raw point with a different metric, CHN.
So I want to fix the Kobayashi metric in this.
Okay.
So it's my thesis advisor used to say that it's better to compare apples with apples and pears with pears, as opposed to apples with pears. So I guess one should compare the Kobayashi metric
Well,
between.
that will not be scaled.
Well. Okay. So the second remark I want to make is that well, in fact, the proof or the technique that is used in the proof, it's well, one can deduce a lot more. So in fact, the theorem also applies. So also proves the same result. For strictly convex domains. Strictly convex domains. Instead of Teichmüller spaces. And that appears to be, well, that appears to be new in the literature, although there's a lot of results in this direction. But previously, well, the work was focusing on, in the literature was focusing on studying the boundary of these domains. And this is something that I was trying to avoid. And all the results in this direction were assuming some smoothness of the boundary. So that's another consequence. And let me state what I think is an interesting generalization of this result is that, well, in fact, every totally geodesic isometry between Teichmüller spaces is geometric. And what I mean by that is that it's either a Teichmüller disk or it's given in terms of a covering construction. Well, it's given as a pullback of a covering. So particularly if you fix a topological covering between two Riemann surfaces, then you can pull back complex structure from the one to the other, and that gives a lot of isometric, totally geodesic embeddings. It can also be seen as fixed point loci of certain subgroups of the mapping class group. And it turns out every total geodesic isometry between Teichmüller spaces has to be of this form. And I think Alex mentioned that yesterday. I think it would be an interesting question trying to classify what other total geodesic subsets of Teichmüller space or moduli space are there.
I'm confused with this covering construction. It's not explored for correspondence.
Yes, at the level of moduli spaces, that's right. Although it doesn't make sense as a map between moduli spaces, which is why I want to think of it as in terms of the. Okay. So, well, perhaps the main interest in studying these copies of CH1 in Teichmüller space comes from the applications to billiards. And the fact that very rarely, but still quite strikingly, there are cases where this Teichmüller disks project to moduli space onto closed, algebraic curves or hyperbolic Riemann surface of finite volume, which are isometrically immersed in moduli space, and the existence of those has a lot of applications. To questions that have to do with the dynamics of billiards. People were interested whether one can have other locally symmetric spaces which are isometrically immersed in moduli space in higher dimensions. So second result I want to mention is that this Teichmüller curves, these isometrically immersed curves in moduli space, they're very spatial, and in fact there are no locally symmetric varieties isometrically immersed in MG for the Kobayashi metric, as long as the dimension is at least 2. Excuse me?
No disk that.
Not isometrically, yes.
But this is like locally, it's embedded or immersed?
It does,
It can have some deception?
yes. So let me state that, well, in fact, I proved more general statements, so let me formulate that in terms of Teichmüller spaces. Let's sort of let well, a Teichmüller space and a bounded symmetric domain with dimension at least 2 so they both have dimension at least 2. Then there are no holomorphic isometries. Holomorphic isometries from the Teichmüller space into the bounded symmetric domain, or the other way around. And here by an isometry I mean the weakest possible sense. Infinitesimally, the differential doesn't preserve the norm. That is the difference.
When you say asymmetric embedding, the dimension may not be the same, right?
Yes.
Okay.
Well, yes, absolutely. So, for example, there's no copy of CH2 in Teichmüller space. And, well, I also prove a dual statement to that. Well, Gen and a bounded symmetric domain of dimension at least 2, then in fact there are no holomorphic isometric submersions either. And by submersion, I mean that the codifferential is an isometry for the dual norms, or more geometrically, the differential takes the unit normal upstairs exactly onto the unit normal downstairs. So in some sense, dimension at least 2, well, Teichmüller spaces and symmetric spaces, they are as incompatible as possible. However, I do want to mention some remarks.
So I don't understand your theorem. Okay. When you say it's a submersion, then the source manifold has a larger dimension than the target.
That's right. So I do not assume the dimensions are the same here.
Yeah, I know. But then so you have 2 points which will be split to 1 point.
Mm-hmm.
But then so how could it be asymmetric?
So I want the unit normal upstairs to map linearly onto the unit normal downstairs, or if you wish the other, well, the unit normal downstairs is the shadow of the one upstairs. So, well, let me state that, well, in fact, a corollary of that is that there are no isometries, or holomorphic isometries, from a strictly convex domain into Teichmüller space for the Kobayashi metrics. Answers the question you mentioned at the beginning. So, Teichmüller space is not a convex domain. Well, it cannot be realized as a convex domain, and well, in a very strong sense. And again, this is it's a direct consequence of this result by a rescaling argument. It's a classical rescaling argument in complex analysis due to Pinchuk. It's not needed. No, it's actually not needed.
Yeah, so is that obvious from the video field? So omega has a complex geodesic, right?
That's right.
And you composing with the F, then you can isometrically embed the geodesic into your Teichmüller space, but your field theorem, you don't have this kind of set.
Well, I already assume these are holomorphic. So the point is either dimension is at least 2 and this is convex. One can, taking a sequence of points converted into the boundary and using the fact that, these burst embeddings have a bounded geometry, one can reduce to the case of CH2. Isometrically embedded in Teichmüller space, or CH1 cross CH1. Okay, another remark I want to make is that
when you were telling that nice amplitude space geometric, does this include that automorphism will be given by mapping class?
Unless it's a Teichmüller disk.
Yes.
Yes. Yes. So the second remark I want to make is that the restrictions on the dimensions of being at least 2 are indeed necessary. So it is known that there are holomorphic submersions onto disks. Holomorphic isometric. And in some sense, these arise from considering periods on Riemann surfaces. So the Teichmüller space embeds, well, there are a lot of interesting maps of Teichmüller space or moduli space into, well, symmetric spaces. So in particular, at the level of universal covers, you can associate to a Riemann surface the Jacobian of any, well, of any of its topological covering maps. And that will give you, well, isometric immersions of Teichmüller space into bounded symmetric domains, known as Siegel spaces. However, these embeddings are never isometric. Well, they're isometric in some directions, in very few directions, in fact, and generically they are contracting. However, in the in the special directions which arise from quadratic differentials, which are the square of abelian 1 forms, or well, certain twists of that, then in this case, well, you can project with the submersion. You can find a projection of Siegel space onto a CH1 that is isometric in the direction arising from the square of an abelian differential, and that's exactly how these isometric submersions arise. And in fact, these are the only examples, well, the only non-trivial examples of how to produce isometric submersions onto CH1 from Teichmüller space. And perhaps one of the sort of the last big open problem in classical Teichmüller theory, well, would be to settle this question of whether, well, given any Teichmüller disk, is there an isometric submersion of Teichmüller space onto that disk, which is equivalent to asking whether the well, this theorem is true for infinite dimensional bounded symmetric domains. Which, and yet another way of formulating that is whether the Kara-Theodori metric coincides with the Kobayashi metric on Teichmüller space.
Isn't that branch along the hyperelliptic ones?
Okay, so
So you mean for the Teichmüller space, the Kara-Theodori metric is the same as the Kobayashi metric?
yes, so this is it's not known. So that I mean, that's to my mind one of the sort of remaining questions that we still don't have a very good idea how to approach.
So you want to prove it, or it's already clear?
No, it's a question.
It's a question.
What's the definition of this?
Oh, the Kara-Theodori metric is the smallest invariant metric in some sense. So it's defined in terms of holomorphic maps out of Teichmüller space. So the Kobayashi metric was the largest metric, so that any disk is. But I prefer to think of this in terms of the question about submersions.
I think we can make the convex statement somehow stronger, that no matter when if you embed a Teichmüller space, then not only it's not convex, but like the boundary should be really crazy. All this or not.
What is well?
Like it's very much better.
What would really crazy mean?
I don't know, like non-convex in a dense set of
So right.
totally non-convex in a dense set of
So well, it's not exactly what you're saying, but a closely related. Well, let me pose this as a question or conjecture. By analogy with symmetric spaces, for any base point, there is a unique convex realization about this point, the Hardy-Chandra embedding, and these embeddings are unique up to change of basis, linear change of basis. Well, is the same true for Teichmüller space and the burst embeddings? So there is, for any base point in Teichmüller space, there's a burst embedding, which realizes as a bounded domain. Does this embedding, the geometry of the embedding, determine the base point? If the natural by holomorphic map in the interior extends to homeomorphism of the boundary, do the base points have to be the same? So I think it's 3 o'clock, so I stop. Well, well, thanks for those of you who are back. So I will. I would like to mention a few more results quickly, then focus on the ideas that go into the proofs, or at least in some particular cases. So let me just very quickly mention a corollary. Well, another corollary of this theorem, which is that the one left on the board. The fact that there are no isometries from bounded symmetric domains for the Kobayashi metric into Teichmüller space, well, in fact, it's well, one can prove that if V is a Kähler manifold, so V is a complex manifold equipped with a Kähler metric, and the dimension is at least 2, then there are no holomorphic isometries totally geodesic. From V to Teichmüller space, where Teichmüller space is equipped with a Kobayashi metric. So that's sort of morally the wrong statement because you compare something completely different. But I did want to.
I would expect that in Teichmüller there are very few round products.
Right. So even infinitesimally, however, let me discuss this. So I will go back to this at. So when I talk about the proof of this result.
Wait, I'm confused. Like Kähler manifold, you mean?
A complex manifold equipped with a Kähler metric.
Doesn't Teichmüller space have a Kähler metric?
Well, there is no holomorphic isometry from this manifold into Teichmüller space equipped with a Teichmüller metric.
Oh, with the Teichmüller, oh, right, sorry.
That's a local statement. It's a small statement.
Actually, well, it turns out, since you asked, that yeah, it should be a local statement. I have no idea how to prove any of these results locally.
What is the statement?
There are no holomorphic isometries from the complex manifold V equipped with a Kähler metric into Teichmüller space equipped with a Teichmüller metric. Oh, you mean what is the nature of isometry I'm referring to?
No, whether V can be a small ball or whether you want it to be compact.
Oh, I mean, you can assume it's complete because this metric will be complete, so you will be able to extend that. So, I mean, I assume it's totally geodesic, so that will not make a difference. But for an infinitesimal statement, it would make a difference. So one can, well, you could sacrifice totally geodesic, the assumption that the map is totally geodesic if you impose completeness and the fact that the holomorphic curvature is bounded, say, from below from -4. And the proofs of this result, they do use the global geometry of Teichmüller space, so I will come back to that. Okay, and another sort of result I want to mention before going into the proofs is of a different nature, and since this is a three-manifold program, why do people in three-manifold care about Teichmüller space? Perhaps the most important applications is to prove geometrization theorems, and so a lot of problems having to do with the existence of a nice geometric structure that can be formulated as a fixed point problem in Teichmüller space. And the Kobayashi metric turns out to be a very useful tool to proving fixed point theorems. So I would like to mention a general result that so any holomorphic map from Teichmüller space to itself, either has a fixed point or every orbit diverges. Sorry, excuse me? It escapes the compact cells. So if there is a recurrent orbit, there will be a fixed point. And again, this is an analog, so this is sort of classically true for CH1, or more generally for convex domains. Usually referred to as the Denzoi theorem. And this has been generalized in the class of convex domains, even in infinite dimensional Banach spaces. However, all of these arguments, in some sense, they do use the fact that the boundary of these domains are very nice and smooth. Whereas for Teichmüller space, its realization as a bounded domain is far from being nice. It doesn't have a nice boundary that you can do analysis on. It's not convex. And so I guess the point I want to emphasize is that the Kobayashi metric is really what one. Yes, yeah, you could diverge in the boundary, and then there's a discussion of what.
I didn't quite understand. Can you say again what orbit diverges mean?
Yes.
It's the same as saying every orbit is unbounded?
Yes. So. So if there exists an infinite sequence of.
So that looks stronger than saying every orbit is unbounded. Because an orbit could be bounded yet still contain.
Either every orbit diverges or there is a recurrent orbit. Right?
So it's saying every orbit is proper.
So no matter which point you choose, if you look at what happens to each iterate, it's going to escape all compact sets. Or you have a fixed point. So it's an analog of the Denzoi-Wolf theorem, except for I haven't told you what happens to the boundary. What's the behavior near the, whether this point diverges somewhere nice in the boundary. And I don't want to do that because the boundary of this Burson embedding is not nice, so it's not very useful to look at it this way. However, this intrinsic Kobayashi metric of Teichmüller space, it's really what one has to use to prove this result. And I should point out that I'm not using, I don't assume that the map is an isometric, it's just any holomorphic map, for example, the skinning map or the pullback map. Okay, so I will.
So your theorem says Teichmüller space has a lot of nature for convex domains. So this result is is special for convex domains.
That's right. So although Teichmüller space as a bounded domain is very different from being convex, it does have a lot of features which which one does see in symmetric spaces or convex spaces. Okay, so right. So I would like to to discuss the proofs of some of these results, and I would like to focus in particular to the explaining why every totally geodesic isometry from CH1 into Teichmüller space it's holomorphic. And why there are no holomorphic isometries from CH2 into diagonal space. So although the proofs are technically very different and they do use ideas from geometric topology, I like to think of them as, well, they're both using at least formally the same, the same idea or the same technique, which is that of complexification and realification. So let me just draw a picture here and then focus on more details. So the idea is to start with a totally geodesic isometry and then try to extend it to a holomorphic map. So we go back to the holomorphic setting where it's easier to study. And somehow the first step in doing that is forgetting the complex structure on CA1 by embedding it as the totally real diagonal in the bidisk by the graph of the identity. And well, in this setting we wanted to do the opposite. We start with a holomorphic map, and the idea is to look at these totally real hyperbolic planes, totally real hyperbolic planes sitting in CH2 as totally geodesic, totally real subsets, and restrict this map. Restrict the original isometry into these RH2s, and then study how, these RH2s sit inside CH2, how they vary inside CH2 in order to show that such isometries don't exist. So I will explain the arguments in more detail. And the first observation is that, so we have a copy of CH1, which is totally geodesic in Teichmüller space, and we don't know that it is a Teichmüller disk, or it doesn't come from from one of these SL2R orbits. However, we know that every real geodesic maps to a real geodesic, which is equivalent to asking that the map is totally geodesic. So this copy of CH1 in Teichmüller space will be intersected by these SL2R orbits everywhere. So there will be Teichmüller disks intersecting this CH1 through every point. And the idea is to organize these, these collections of Teichmüller disks using the bidisk. So there's a foliation of the bidisks by holomorphic copies of CH1 arising by looking at the graphs of reflections along the disk. So for any unoriented geodesic, it's the fixed point locus of a unique anti-holomorphic reflection along this geodesic. Hyperbolic reflection. It is an anti-holomorphic involution. And I denote by R the collection of these holomorphic involutions on the disk, which I can think of as parameterizing unoriented geodesics. Now the graph of any such reflection is going to give you a holomorphic copy of CH1 inside the byte disk. That's just simply because I've chosen the opposite complex structure on the second factor, so that I get a holomorphic map from the reflection. However, this is a singular. Well, that's a singular foliation. Simply because any two of these disks, well, the leaves might intersect on the real diagonal. And that will happen precisely when the two geodesics I'm considering intersect on the disk. But that's the only problem. So in particular, in the complement of this totally real diagonal, this is a non-smooth foliation by holomorphic leaves. So the existence of the map from CH1 into Teichmüller space allows us to canonically extend the map into a bigger, into a well-defined map on this byte disk that agrees with the original map on the diagonal, simply by taking the unique Teichmüller disk that agrees on the leaf, that agrees on the graph of this reflection with the Teichmüller disk. So there's a unique Teichmüller disk given in terms of a holomorphic map from CH1 into Teichmüller space, so that along the geodesic gamma agrees with the map F. And that gives you a recipe to extending this map leaf-wise into a map defined on the byte disk. It's a graph of a reflection.
But you didn't work reflection.
Yes. The reason is because, the image of the total geodesic isometry will send every geodesic on the disk to a geodesic in Teichmüller space. This geodesic in Teichmüller space arises from a Teichmüller disk, from an SL2R orbit, extends, if you wish, to a unique holomorphic disk inside Teichmüller space. And these unique holomorphic disks is what this the restriction of F on the leaf gamma R is. So there's a unique way of doing this, of defining this map.
I have to prove something to show that this map is holomorphic.
Oh yes, of course. I haven't proved it. I've just constructed one map that extends the. So this map has the property that it extends the original map on the diagonal, on the image of the total real diagonal, and is holomorphic leaf-wise, right? And then the basic lemma here, claim, is that, in fact, if F is totally geodesic, then it's real analytic. And that's not necessarily well obvious, in particular because the Teichmüller metric, the Kobayashi metric, it's not a real analytic metric. However, well, there are several ways of deducing that. And perhaps the simplest way is, well, one can use a trick that has to do with the Klein model of hyperbolic space. So there's a real analytic identification of the Poincaré model of the hyperbolic disk with the Klein model in such a way that in such a way that the straight lines are actually, they are unparameterized geodesics. And the existence of a nice coordinate chart for which all vertical and horizontal lines are unparameterized geodesics, allows one to very easily deduce this real analyticity from some classical results in complex analysis. Having to do with a separate analyticity of real analytic maps. So I guess I'll be happy to sketch the details of that, but I will leave it for the time being.
Small f is total geodesic?
Yes.
Or
No, if small f is total geodesic, small f is real analytic. Right. But that will tell us that f extends uniquely to a holomorphic map near the total real diagonal. So there's a unique germ of holomorphic maps defining the total real diagonal in the bidisk that extends the map F. And I've already given you one map that has the property that is holomorphic along every leaf. So that has to be the unique map. These holomorphic leaves intersect the total real diagonal along real geodesics. So the restriction of the unique extension, holomorphic extension, has to agree at least locally near the diagonal with the map I just defined. And then you can just use the leaves to extend this to holomorphic map defined globally on the bidisk.
So how do we use this picture to show that it's real analytic? This picture, these are unparameterized? I didn't get the argument.
Okay, so there's a very general theorem. If you look at if you look at the square, the unit square in R2, and you embed it in C2 as the totally real subset, and I want to have a solid cylinder where I extend every vertical segment to an ellipse of definite eccentricity in one of the directions. And I want to look at the transverse picture as well. So that sits inside C2. So the pink picture sits inside here. And then the yellow picture or the green picture. So I want to do the same thing for every horizontal disk as well. I have two solid cylinders that intersect in C2, that intersect transversely along the totally real unit disk, and they are such that they are foliated by holomorphic disks. in these two two transverse directions. Well, the theorem is any holomorphic map any map, any function f from the union of these two cylinders such that is holomorphic on every ellipse, either in one cylinder or the other. It's holomorphic on every holomorphic. Then it has to be real analytic, and in fact, it extends to a holomorphic map, a unique holomorphic map in a neighborhood of these two three-dimensional cylinders in C2. So that's a classical, result from complex analysis. There are way more strong theorems known these days, perhaps theorems due to Schiffer that allow you to transport analyticity in a sort of much more general setting. However, the proof of this result is extremely elementary. It is actually a very fun exercise. Using,
So is that kind of a Hartox phenomenon?
Yes, it is a Hartox phenomenon. Yes.
Hartox.
It's not the theorem of Hartox, but it's related to that.
It's kind of.
Mm-hmm. Okay, so sorry, is this clear? Is it clear how this result implies the lemma? Sorry. So I have chosen coordinates in I have chosen coordinates in this in the hyperbolic disk, so that the vertical and the horizontal lines are all unparameterized geodesics,
Right.
and the time parameter depends really analytically on the distance. So for each one of them, there will be a Teichmüller disk that extends that geodesic. And similarly, for every vertical, there's a Teichmüller disk. And the map I've defined has the property that's holomorphic on these Teichmüller disks, both vertical and horizontal ones. So we automatically, in the way I formulated the result, it automatically.
Well, it extends a unique holomorphic map, then you have to show that it agrees with this map.
Well, but it has to, because I've constructed this map so that it's holomorphic on the leaves of this foliation, and these are the Teichmüller disks. Two holomorphic maps that agree along a real line, they have to coincide. Well, yes. Well, little f is real analytic, and therefore f is holomorphic near the real diagonal in the bidisk. And once you know that, you can just write down the power series expansion. You can see that the property that the leaves are holomorphic, the CH1 copies are holomorphic, allows you to deduce that the full map is holomorphic on the bidisk. And let me just say that, that's in some sense a trick to hide the work of proving the theorem under the carpet. There is a way of proving this in terms of period coordinates, for example. and using the reanalytic implicit function theorem. But the argument is it's far too messy. And that's a nice way of seeing it. Okay, so now we know that we have this holomorphic extension, and it's not clear what to do with it. So in particular, let me draw this picture for the. So the vertical or the horizontal slices in this disk, they don't necessarily have to be Teichmüller disks, because these extensions, they were not defined in a way that they correspond to this vertical. However, there is a nice property that this foliation has, which is that a point z, w lies in the leaf gamma r, if and only if the point w, z lies in gamma r. And in some sense, this is, that's a trivial observation having to do with R, the fact that R is an involution. But in some sense, this is really what, one needs to deduce that this map is degenerate. So the goal will be to prove that this map is degenerate, so the image is one-dimensional. And using this property, we can sort of conclude that either some vertical slice or some horizontal slice will be essentially proper. What do I mean by that? So by essentially proper, all I want to say, I want the set of rays, radial rays, from a fixed base point to diverge in Teichmüller space almost for a set of positive measures. I want to have a holomorphic map from the disk into Teichmüller space with the property that the radial rays for which diverges in Teichmüller space it's a set of positive measure. And and why this is the case, that follows precisely because the distance from z, w to the point w, z for the Kobayashi metric on the bidisk is the same with the distance from z, w on the disk. Simply because both points lie on an isometric copy of CH1, which is it's a total geodesic holomorphic isometric copy. So you know that these 2 points are really far away, as long as z and w are far away in the CH1. If you fix one of the points, say z, and you let w as the center of the disk, and you let w converge to the boundary of the disk radially, then there will be corresponding points lying either in a horizontal or a vertical slice that will diverge in Teichmüller space, simply because these 2 points cannot stay in a compact region in Teichmüller space, or the image of these points, which is what is necessary to to show that either some vertical or some horizontal slice has to be essentially proper. In fact, for a set of rays that has measured at least half of the rays. Okay, so once we know this fact, then one can ask what happens as you vary these disks into bidisks. So the theorem of Sullivan if the map is essentially proper, it's a holomorphic, essentially proper then you cannot vary this in a holomorphic family. So I have a holomorphic disk. I have a map from a holomorphic. I have a map from a disk into Teichmüller space, which is holomorphic, and then I want to look at the radial rays. For which this is unbounded. So this diverges. And I want this set to have a positive measure, linear measure. So I want to have a positive set of angles for which this happens.
It depends on choosing analytic.
Excuse me?
It depends on choosing analytic.
No, if it's true for one point, it will be for any other point of the disk. So in the interest of time, let me not explain more about how Sullivan's rigidity theorem relates to this. So any holomorphic family is trivial. So there's no way to move a family of disks holomorphically. Yes.
Does this imply holomorphic rigidity of Teichmüller curves in MG, which is something McMullen proved?
No, there is more. No, there is more to. Yeah, it does simplify Kurt's argument, McMullen's argument for the rigidity of Teichmüller curves, but in that case, it's a little bit more complicated because you want to move both the curve and the map at the same time. But no, it does give a sort of more direct way of deducing
But
the
you
theorem.
can always reparameterize that, right? So you're up to reparameterization here.
And this is really a theorem about three manifolds. So the Sullivan rigidity theorem has to do with the fact that so one can look at this. The Beers embeddings correspond to certain quasi-Fuchsian three manifolds, and the geometric limits of these three manifolds as you hit the boundary of Teichmüller space, it turns out to be rigid. So you cannot deform. Well, there's no invariant manifold supported on the limit set.
Because we can reparameterize
Yeah, yeah.
side
Yeah,
after reparameterization.
yeah, up to reparameterization.
No, I think the way I said it is fine.
No, you can reparameterize F0, you get a family.
I don't know how to get a holomorphic family. How would you do that?
No, so you just use automorphic rule for the delta.
You start
It's a
with
three-dimensional
you
theorem.
map
It's not
this
holomorphic.
to a smaller one, or with another morphic.
No. No, the CH1 is fixed. I have a fixed holomorphic map from CH1 into Teichmüller space that depends holomorphically in a parameter T. Or if you wish a holomorphic map from the bidisk, so that at the origin it's proper, then all of them have to agree that you can't reparameterize holomorphically. So that's
The FTs don't have to be essentially proper, just F0.
just F0. It follows that FTs have to be also because
Or you have
but even worse, the fact it's the Kobayashi on the metric on the byte disk, it's the submetric. So any two parallel slices are bounded distance apart. So that's that essentially goes into the proof.
Yeah. So you want this depends holomorphic on the parameter. That's
Yes. So it's a holomorphic family.
Okay.
Okay. So so in particular, so we're given that we are now done. So hence. Since either some horizontal or some vertical slices are essentially proper, we know that either all either all the horizontal slices agree or all the vertical slices agree. So for the image is one-dimensional, and therefore it has to be a Teichmüller disk. That also explains where this holomorphic or anti-holomorphic condition comes from, and that has to do by the choice of the conjugate complex structure on the second factor. So depending on which condition happens, I mean, the first condition will give you an anti-holomorphic disk, and the second will give you a holomorphic disk. Okay. So let me. Let me not write this down, but let me say this in words, that this is closely related, at least at some formal level, to the proof of the geometric Safarevich conjecture. Where one studies holomorphic maps from a fixed algebraic curve into moduli space by looking at the map from the universal cover into Teichmüller space. Then the action of the monodromy on the disk is replaced by this by geodesics on the disk that map to Teichmüller geodesics. And so by these SL2R copies that hit the boundary and they converge to a set of positive measure of the ideal boundary of the disk. And in fact, formulated in this way, one can very easily relax the conditions of being totally geodesic by just assuming that there is a family of geodesics that trap every point in the ideal boundary that map to Teichmüller geodesics into Teichmüller space. And again, the Salver rigidity theorem is what comes up in the the Teichmüller theoretic proof of the Safarevich conjecture, the geometric Safarevich conjecture. And I do want to point out something, that this idea of complexifying Teichmüller disks, at least in the classical Teichmüller theory, it hadn't been appreciated, but one can deduce a lot more interesting and other results in this direction. So for example, the same argument can be used to prove that the automorphism group of Teichmüller space with the WP metric has to be the mapping class group, which is more or less immediate if you use this complexification approach. Okay, so are there any questions about the proof? So next I would like to explain why there are no holomorphic copies of CH2 into Teichmüller space. Then the idea here is to forget the complex structure by studying these totally real slices. So any holomorphic isometry from CH2 into Teichmüller space will be necessarily totally geodesic isometry as well. And what I want to do is restrict in a totally real copy of RH2 sitting inside CH2 and look at the geodesics, a pair of orthogonal geodesics generated by quadratic differentials, xp and x comma q. So this will be Teichmüller disks associated to the pair of orthogonal geodesics starting from a base point x. So this totally real slice moves, well, there are a lot of these slices sitting inside CH2. For example, one can fix the geodesic and vary the other one along the Teichmüller disk. So there's a whole family of those copies of RH2. And the idea is to study how does this family map inside Teichmüller space. So well, let me just state that if you choose these directions generically inside these Teichmüller disks, in the Teichmüller disks, it's possible. Well, if the directions correspond to uniquely ergodic measure foliations, then the property of the horocycles for these foliations can be, well, the complex hyperbolic horocycles can be described explicitly in terms of the geometry of the Teichmüller metric. No, I proved that they are holomorphic when they're equipped with a Kobayashi metric. So the curvature here is more flat. For example, any total geodesic map from CH1 into CH2 with a Kobayashi metric is holomorphic. However, there are a lot of RH2s sitting inside the CH2. So for any quadratic differential, there is a pair of measured foliations given by the vertical and horizontal lines in the plane when you presented the quadratic differential as a polygon. And the Teichmüller geodesics have a very simple form. So the Teichmüller geodesics, they simply correspond to rescaling these foliations. The actual geodesics can be very simply described in terms of measured foliations, but it's not clear how the foliations change when you move the direction inside a Teichmüller disk. And this is what essentially I want to use from this picture. The fact that the geometry of this, well, the geometry of CH2, or rather the symmetries of CH2 would allow you to prove that the way that the measured foliations change as you vary in the disk is not compatible with what happens in reality. So it turns out that the corresponding quadratic differential on the Riemann surface obtained on this horocycle will have vertical measure foliation equivalent to the one arising from the original base point. And using this fact for both of these directions allows you to compute the distance between these 2 points in terms of the geometric intersection pairing of measure foliations. is so. In particular, the distance between these 2 points will be described well in terms of this formula, and then you can start varying one of the quadratic differentials along a Teichmüller disks, and then observe that this distance will not change simply because, well, the map z comma w going to z comma e to the I theta w is a holomorphic isometry for CH2, and that will preserve the geometry of horocycles and the corresponding distance obtained by looking at the unique geodesic, which is asymptotic to both endpoints, and AB will correspond to the intersection of the geodesic with the 2 horocycles. You mean for the previous statement? It will almost work, and in fact that's why I started thinking about the question in the first place. Except for the one technical remark, which I don't know that there will be directions that will be uniquely ergodic. So there's a pathological case where this isometric disk will be proper in moduli space, and then it's not clear how the geometry of these horocycles relates to the geometric intersection pairing of measured foliations.
How did you get the distance between the intersection between the formations?
Right. So for well, you can ask what well, for any Riemann surface there will be a unique geodesic, Teichmüller geodesic that converges and will be positively asymptotic to the fixed geodesic, to this horizontal geodesic. And then you can ask what is the quadratic differential, or rather what's the measure foliation of the quadratic differential generating this geodesic. And then if the original geodesic was uniquely ergodic, then it would follow that the measure foliation will be the same measure class with the original one, which is a theorem of how we measure.
Yeah, but what if it's not uniquely ergodic?
Right. For example, if it's well, it's completely periodic,
Right.
then they will never be positively asymptotic, unless they are on the same Teichmüller disk.
So you need this only for some special points, the distance relation between the distance?
For the generic. In fact, yes. So in fact, if I knew this for if I knew this for 1 point on this on 2 orthogonal disks, then it would be fine. Okay. However, that's well, that's impossible because one can prove directly that. There's an explicit formula for describing the geometric intersection pairing that uses the fact that these foliations, they all arise from a fixed flat metric. So you can choose geodesic representatives for a geodesic representative for any measure foliation in this flat metric, and then you can compute explicitly this geometric intersection pairing by integrating the holonomy vectors for these geometric representatives. So there's an explicit formula that shows you that this quantity is never constant. It can never be constant, so it always depends on the angle, which is not compatible with the symmetries of CH2. Okay.
Can I ask you why didn't you just try to use, or have you used part A for part B? You have all these.
No, I did. No, the arguments are technically completely different. They're not related to each other. However, there is an approach. There is a way of trying to prove the fact that there are no CH2s in Teichmüller space using a similar method.
Wait, so I would have tried to like use the complex hyperbolic planes inside of CH2. Those go to Teichmüller disks and then try to get some contradiction out of that somehow, I guess. But, is this saying something about like the Finsler norm, that there's no, the Finsler norm of CH2 doesn't sort of isometrically embed in the Finsler norm of Teichmüller space at any point?
Right. So yes. So let me comment on that. So I apologize. Well, I probably brushed through some of the details. And, they're probably clear to the experts and not so clear to the those who are not familiar with this description of Teichmüller geodesics. But I'm happy to discuss any details. Any points in more detail. But let me just briefly comment on the infinitesimal picture. So both of these arguments, they do use a global geometry of Teichmüller space. You use the asymptotic behavior of geodesics. The question is what happens infinitesimally. Let me just state a problem. Well, are there any linear round slices in the tangent space equipped with a Kobayashi metric? So are there any CH2 equipped with a round metric, linear, sort of C-linear isometry into the tangent space of Teichmüller space with a Kobayashi metric? So I don't know the answer to this question, unfortunately. And, that's the most natural way of perhaps addressing this problem. So it will simplify a lot of these results. But I do know the answer to the dual question. There are no round slices. So for any Riemann surface, for any point in Teichmüller space, or moduli space, the dual Kobayashi norm is given in terms of the L1 norm of the space of holomorphic quadratic differentials, and then there exists no linear round slices. And that is essentially what is used in the proof of the results about submersions. So that's a much easier problem to study because there's an explicit way of what these norms look like. However, this question is difficult because it asks something about projections. So any convex set up here will be take any curve, any convex subset of this cylinder, and then take the convex hull of that inside the cylinder. Will define the norm, which will project onto a round norm in C2. And this could be as complicated as one hopes. So it's studying projections isometric projection is a much harder question in general. But let me mention in brief that the geometry of this norm in the space of correct differentials was essentially what Royden used to prove the fact that the automorphism group of Teichmüller space is the mapping class group, and So the beautiful result that he showed was that the norm itself is an invariant of the curve x. So any linear isometry between these vector spaces for two different Riemann surfaces equipped with their L1 norms, it necessarily comes from a non-constant holomorphic map between the Riemann surfaces. So P is to the I theta. And well, it's interesting that one can generalize these results in several directions. So I mentioned in the previous talk the fact that totally geodesic isometries between Teichmüller spaces are geometric, and the way the way to prove this result is by studying linear projections arising isometric linear maps, which are isometric linear projections between these norm spaces for two different Riemann surfaces necessarily have to be of this form. So since I'm out of time, I will not talk about this any further.